So we are dealing with the 14th problem in this series, and the 14th problem is problem number 1.92. The problem is asking a chain of mass m forming a circle of radius r is slipped on a smooth round cone with half angle theta. Find the tension of the chain if it rotates with a constant angular velocity omega about a vertical axis coinciding with the symmetry axis of the cone. So as we start solving this problem, we need a diagrammatic representation of the situation which the problem is asking us. So this is the correct diagrammatic representation of the situation shown. The chain over here is marked in this color, which is different from the lighter shade which we are using for the cone, which is rotating with angular speed omega. Now it is of radius r. So over here on this side we are just drawing this chain again. So in this plane we are identifying the forces, which is the tensional force which is to be determined. Now the important aspects that need to be understood over here is that this mass is going to experience a force which is in this outward direction, which is given by dm omega square r. So this is the force which it is going to experience, dm omega square r in this direction, and the tension developed in this chain is T. Now apart from this, it is very important for us to understand that the cone is not a vertical wall, neither a horizontal wall. It is a slant wall, and it is making half angle theta. This information is also given in the problem, half angle theta. So over here, if we think in terms of the normal reaction force, so the normal reaction force is going to be perpendicular to this wall of the cone, which we mark as normal reaction force N, and if this angle is theta, so we can identify that this one is also going to be theta, and the component of force can be considered over here as N cos theta, and this one is N sin theta. So the first thing that we need to understand is the forces which are to be balanced, and again over here the patch which we have marked will be having its weight in the downward direction, so which we are marking as dmg. So it must be kept in mind that all the forces which we have drawn so far will be solved together. Just for convenience, we are drawing the forces in two different diagrams so that we can understand how this normal reaction force is going to act, and how the tension is going to be generated in this rotating chain, and the forces which the chain will experience because of its own weight, and then omega square r. Now the next thing that we do is we break the component of tensional force. So tensional force can be considered in this way, that the two component will be in this direction. This is T sin d alpha, this is again T sin d alpha. Now we are omitting, or we can draw this is T cos d alpha, but the cos component will eventually be cancelled, and this is again T cos d alpha. This is in the vertically downward direction, and it is not in the plane of T cos d alpha. This is the weight of the chain which we have considered dmg in this direction, and all the other forces which we have constructed is in the plane of this ring. So this must be kept in mind. So now if we start solving this, the first thing that we do is we calculate the value of dm. So over here the chain is of mass m having radius r. So therefore we begin with this way, that the mass m is having radius r, that is 2 pi r, and this is equal to dm upon the total angle it is subtending is 2d alpha. So the arc length is going to be twice of d alpha multiplied by r. So therefore from here we can write that the mass dm is equal to m by pi d alpha. So this is the value of dm that we have. Now if we start balancing the forces, so the first thing that we do is we balance force in the vertical direction. So n sine theta in the vertically up direction must be balanced by the weight of the chain in the downward direction. So we are referring this as y axis. So summation of force in the y direction is to be equated to 0. So over here the first expression that we have is n sine theta is equal to dmg, and if we put the value of dm, we have m by pi g d alpha, and this is equation number 1. And now if we apply the next equation, that is summation of force in the x direction equal to 0, so we are balancing forces in the plane of the chain. So in the plane of the chain, the force dm omega square r is in the positive x direction, n cos theta is in the positive x direction, and they both are balanced by 2t sine d alpha. Now over here d alpha is small, so therefore we write 2t sine d alpha can be written as 2t d alpha. So for very small angle, sine of theta can be written as theta. So therefore over here if we balance these forces, then we can say that in the inward direction, that is 2t d alpha, this is equal to dm omega square r, dm omega square r plus n cos theta. So this is the next expression that we have. So over here if we write in terms of n cos theta, so n cos theta can be written as 2t d alpha minus, so dm can be written as m by pi d alpha r omega square. So this is the second expression that we have. Now the problem is asking us to solve for t. So we have these two equations, and now what we do is we divide the two expressions. So we will cancel out n, and therefore on dividing the expressions, on dividing the equation 1 and 2, so we can remove out n sine by cos can be written in terms of tan theta. So tan theta equals m by pi g d alpha upon 2t d alpha minus m by pi d alpha r omega square. And over here we are solving for t, and hence on solving we obtain the value of t turns out to be mg by 2 pi cot theta plus omega square r by g. Omega square r by g. So this is a very interesting problem where you need to understand all the forces, the plane in which the forces are acting while solving this problem. And this was problem number 1.92.